Let's take a look at this example for acceleration in one dimension. When you are driving, if you had to stop quickly, you have a reaction time of about a quarter second. We also know that at 60 miles per hour, you could stop in a 50 meters at maximum deceleration. How far would it take you to stop if you were going 75 miles per hour instead? The first step is always a picture. What does this mean? What does this reaction time have to do with the problem? Well, at the initial t is equal to 0, we imagine you see something and you're trying to stop as absolutely soon as possible. But there's a quarter second before you can do anything. That's your reaction time. So there's this quarter second initially where there's no acceleration. That's the gap between when you decide you want to start before you actually do anything. Then you apply the brakes and you come to rest, and during that time we're going to say the acceleration is constant. Okay, I want a coordinate system. So I establish my 0 at the point where we want to start the process. I'm having positive x go to the right, and the total stopping distance is 50 meters. Now you're going at a higher speed. What does that mean? Well, the reaction time doesn't change, so that's still there. But of course, you're going to go a little further during that quarter second because you're going at a faster speed. Then you decelerate and finally come to a rest with a total stopping distance of x. And of course, that will be longer because you started at a higher speed. We just don't know how much. One thing we will observe, though, is that of course the acceleration is also going to be constant. You have the same car, you're still applying the same brakes under the same conditions, and so the acceleration will be the same in the two instances. So we have an idea of what's going on. What sort of physics should we apply to the problem? We have two situations. The acceleration isn't constant throughout, but it's constant in pieces. We also know the total displacement in the first example. We want to know it in the second. This problem is begging to use graphical methods to try to solve it. Let's take a look at the velocity versus time graph. In velocity versus time, there's an initial quarter second where you're going at constant speed, and then with constant acceleration, the velocity is a straight line down to 0 at some total time t. The first thing I'll do is convert to SI units. 60 miles per hour is about 27 meters per second, so that's the initial speed. Next, I know that the area under the velocity versus time curve is the total displacement, which is equal to 50, so let's just calculate that to find out what happens. So 50 is equal to the area of that first rectangle, which is base times height, times the area of the next triangle, which is 1/2 base times the height. And the height is still 27. The base is this time interval, delta t. And that's really useful because if I have that, since I know this height of the triangle, rise over run gives me the slope of that line, which is the acceleration. And so here we can now calculate that base, and I calculate delta t, which is 3.2037 seconds. I keep the significant figures so I don't lose significance in rounding errors and internal calculations. I can now calculate the slope of the velocity graph, and that's going to give me my acceleration. The acceleration is negative because the velocity is going in the positive x direction and it's slowing down. So negative the rise over run, which is 27 over the time difference I calculated, and I get an acceleration of negative 8.428 meters per second squared. So this is great. I now know the acceleration, which is going to be the same acceleration in the next step, as well as the reaction time is going to be the same. So let's go ahead and look at the higher speed now. So I have our picture and our velocity graph. But now let's look at the green curve. Again, there's an area of constant speed and then constant deceleration. In this case, I had 75 miles per hour, which converted to SI is 34 meters per second. The acceleration I already know because that's going to be the same for the same car, and that's from before. And that acceleration is going to be rise over run. If I were to just calculate the slope of this graph, and so that's going, since I know 34 is the height, this will allow me to calculate this final time interval. And so I plug in those numbers, and I find that final time is equal to 4.0342 seconds. So now I can calculate the area under this curve, which is going to give me the final stopping distance. The area of this first triangle, base times the height, 34 times a quarter, plus the area of this triangle, which is 1/2 the base, which I just calculated, that time interval, times 34. Those are the results my calculator gave me, and the answer then is 77 meters, which is quite a bit larger, more than 50% more than the previous example, which was just 50 meters, even though the speed only went from 60 miles per hour to 75 miles per hour. And that may seem a little surprising, but it's not completely unreasonable. We have the same sort of order of magnitude, so we should have some confidence that we did the calculation correctly and some wariness of driving too quickly.